Green's theorem. Everybody know Green's theorem, right? We've seen it. So they formulated like this. See if this makes sense now. Line integral along a curve, a closed curve, right? Is this always 0? Line integral along a closed curve? Not necessarily. If it is conservative vector field is 0, but arbitrary vector field is non-zero, right? And this is converted to a double integral over a region. Okay? What was the motivation of this line integral? What was the very motivational problem of this line integral? What calculation? Work calculation. What was the very motivation of double integral? The very beginning, how is it motivated? To compute volume, right? Or in the physics sense, usually total mass or something like that. So work done by that is mathematically connected to double integral, some sort of volume or density. That's strange, right? But mathematically, this magnitude of this work calculation is connected with some double integral. Okay, so let me show you that statement again. This is the full statement. Since you have practiced about 3 times with this example, I hope you're kind of familiar with this thing. So let's look at left-hand side. And here's a curve C. Described there as a curve is this boundary. Region D, which is inside there, is everything inside there. If you look at left-hand side, there's no need to consider about region D, right? This is the line integral over what? Again, it's a line integral of a vector field with P and Q component. All you need is this P and Q is nicely defined along the C, right? But the right-hand side requires double integral, right? And whatever this formula is, to make sense out of this double integral, we require everything inside must be defined, right? If it is undefined, how can you even do the double integral, right? You have to close up, and it's a complicated issue if you try to do it. So it is safe. If we just assume everything inside this region is all defined, this vector field PQ, then the right-hand side makes sense. And they're claiming they're equal to each other. Before we say equal to each other, there is a sensitive issue of everything inside the D must be defined to even just to consider the right-hand side. And they're equal. Left-hand side, no need to consider anything about inside. Right-hand side, we need that. And then if it's okay, it's done. So for example, remember that phi in the homework is 0, 0. That was the only spot problem, right? If the region is really over there, we're okay. That vector field we considered before is really the gradient vector field here, because it's defined everywhere except in here, right? So if I choose that P and Q in the left-hand side, what was the answer? Right. But if you go around the closed loop and do the integral, what happened? 0, because it was a conservative vector field. So left-hand side is going to be 0 for that example of the homework, right? Okay? Let's look at the right-hand side. What is this qx minus py? That's exactly the curl, right? You check that in the part B, or second part of the homework, that the curl of that vector field is 0. So the right-hand side inside here is a 0, of course, right? Therefore, integral, double integral over 0 function, of course that's 0. But indeed, that's a proof. If you have a curl being 0 all the time, within that, right-hand side is always 0, right? So if you choose all the closed curve, you want to show the curl is 0. You want to show this is always a 0, because curl is 0. Right-hand side double integral is always 0, because the curl itself is 0. So that proves that if the curl of this PQ is 0, this line integral over closed curve is always 0, which was the equivalent condition for path independence. Remember? The 3 path independence, conservative, and all the closed integral over closed curve is being 0. So if the curl is 0, this statement says the line integral is always 0 over closed curve. Therefore, is path independence. So this is quite elegant proof if we understand why Green's theorem is true. Make sense? Is that I stated as main application of one application of this Green's theorem toward the line integral. quite interesting. If the curl, which is qx minus py, you check that. If that's 0, you want to conclude that's a gradient because of this. It proves it if everything inside D is okay. All right? So does the application make sense? This is a proof if we use the Green's theorem. One notation here is that if you just focus on this region, the problem is more described in terms of this region D, and we denote this boundary curve with this partial D. That's a standard notation for boundary of this region. It has nothing to do with a partial derivative. It's just a notation for the boundary. Okay? But if you start from curve C, then you usually have to use different notation of D. But if you start from region, you want to describe boundary out there, they often use this notation. Right? So instead of C, you can throw in notation like this. It means it's boundary with the counterclockwise from inside. Yes, sir? Let's see which one you're talking about. So that's that. This is example 1. And this is example 3. And this is example 4. Is this one that you're talking about?
No, it was one of the circle ones.
This one? I think it's 1, 3, 4. That's the same.
It was that one. Yeah.
That one, yeah. It's Green's theorem too.
Because the answer was just, it was like pi r squared.
Right. So, for example, if I use that one, let's go through. So disk as unit disk. So here's a disk inside. This is called D. The circle C is also denoted like this one, right? So that circle around the C of x times dx plus xy times dy, right? This is the double integral over this in a complete disk. Here's a qx, right? That's y there, right? And py is a 0, so it's a dx dy. Correct? So it's integrating this one, right? And the region is this circular region, so I guess polar coordinate change is convenient, right? Yeah.
But they ignored all that and just said now multiply by the area of the circle. I'm not sure if that was like a theorem or something that I missed.
I think what they did, they didn't do the change of the variable. They did the iterated integral, right? Iterated integral -1 to 1, and this y going from negative whatever, this 1 minus x squared, positive 1 minus x squared, then y, if you do dx first, let me do the y there, and a y there, and dy. That's iterated integral, right? Then this is constant for dx. Then this becomes -1 to 1. So it's a y times x. That's a 2 times... No, that doesn't work.
It's
Yeah.
example 3 now.
Because I mean, it was like 8 times it really briefly said now multiply by the area.
Oh, this one? Oh, yeah, this one, yes. That's what it is. So this one's easy to explain. Where are you going? Confused about the keystrokes. I think I just deleted one file without knowing how this thing works, but I think I remember that this is not it. So example 3 was phi of was that x minus y? Was this one? Y minus xj. All right. If that's the case, that line integral of this one is the same as y dx minus x dy, right? Circle C, correct? And this one go in, and region D. If that's a circle, if you do that, and this one gives you negative 1 and negative 1, right? It's a d x dy, is that right? So that's a constant. You can go outside, and there's a 1 and dx dy, right? So if the density, if you think about this one as a density, if the density is 1, if it is triple integral, if the density is 1, if you do the triple integral, what does that mean? Volume, right? If it is a density for the region, if the density is 1 for double integral, this represents the area itself. This itself is the area. If it is constant, you pull out. If the density is 1, that whole thing is simply just area. But if the density is non-constant, it changes. In this region, density is different. Over there, density is different. Then you have to integrate. But if density is a constant, all you have to do is the density times the area of the entire thing will represent the mass of that plate, for example. But it is really the area that really governs the magnitude of the mass of the object. So they just related, this is the area. All right? That's the next application. Make sense? Okay. All right. Next thing I want to talk about is this main application of line. This is something we have done already in an early example. That's one application, proving the conservative or not and things like that. But if you have a line integral problem over the closed curve, regions like this, regions like that, and regions like that, and then you have to come up with a formula of this 4 different segment, formula of this 3 different segments, right? Formula of this 4 different segments, and go through long and tedious calculation of the line integral, right? Well, what else can you do? What's that? Double integrals, Green's theorem, right? If you do that P, if you have a line integral like this, I ask you to do that. I didn't say anything else, and then you immediately think, oh, I'm going to use Green's theorem, right? So I'm not going to actually calculate all 4 boundary, but I'm going to enter Green's theorem like that is in region D, and calculate qx minus py and dx dy. I'm not going to ask you to use the Green's theorem. It's your choice, right? Have to make. Oh, Green's theorem is better. Once you enter Green's theorem, the double integral over that region, super easy, right? This one, anybody know how to handle this one? What do we use? What method do we use for this one? Jacobian, change of variable, quick too. This one we haven't done, but this is also easy. But since this and this is what we've done, and that's going to be the contender for our test problem. Make sense? Compute this line integral, period, and then you actually, oh, I can use Green's theorem to enter this one and take care of this integral really quickly. You've seen those 3 examples in the homework. Yes, sir. This line integral and that line integral, that's what you mean? This C indicates the all thing together. C1 plus C2 plus C3 plus C4 with orientation correctly done. That's what this C means. Yeah. All right? So we have done that. And discuss this examples. So let's skip one. So here is what Andrew talked about in here. Just formulate it slightly different. This reverse application. If you have to compute double integral, if you have to compute the double integral of regions like this, for example, it is given by parametric curve, or circles like this. If you break this one down, you have to use a square root, but there is a convenient, very convenient parameterization of this boundary, right? Using sine and cosine if it's a circle. If that's the case, or if the region is looking like this, if you try to double integral, you have to divide this multiple region. You can see it's not meant, but it could be simply given by very, very simple parametric equation using sine and cosine. Maybe it creates like that. And if your goal is computing the double integral of this one, and you can use a Green's theorem to turn that into a line integral, right? So it's this reverse application. Before we looked at the weird bounded line integral, use the double integral conveniently. So if the double integral looks ugly like this, and go to line integral and do that. All right. So to computing the area, the idea is this one. We already saw that. Over that entire region, D. This measures the area, right? Then you can actually compute. Look at the boundary. This notation D, right? boundary of whatever this p dx plus q dy such that the curl becomes 1. Any choice of vector field PQ such that its curl equals 1 will compute the area, right? So look at here, my simplest example in here. This is 0 dx plus x dy. Is that correct? What's inside? Because dx part is missing. What is the curl of this one? Qx, right? Is 1 minus py is 0 is 1, right? So Green's theorem says this one will be the area. This line integral will be the area of this guy. If I have a very easy parameterization of this. This is very, very easy integral. If you have nice formula there, just compute that. And let's try this one. What is the curl of this one? This is qx is oh, they swapped it around. It's confusing. They swapped around d and x in there. So this is q there, right? Because that dy came first. So there's 1 minus. That's another one is minus 1. And there's a half in there. That's 1. If you try this one, also 1. So there are actually multiple versions, not these 3. But this, to me, is the simplest one. Why would you bother with a complicated thing like this? This is the simplest one, right? It's magic. Here's an integral, and you double integral. Then all you have to do is this weird line integral, and then it's going to give you the area. So let's try the example. X dy is easy to remember, right? And you can always check. The curl is really easy to compute. So let's begin with some fact that everybody knows. The area of this region closed by D, right? What is it? Pi r squared. No, right? That's the area. So that's this region D and area the dx dy. No, not an exercise. After this one is going to be exercise. So what is the Green's theorem? The boundary D, that's a circle, right? What goes in here? Any of the 3 choices, right? X dy. Okay? All you have to, so how do you compute this line integral? Think about how you compute line integral. You have to come up with your own parameterization of the boundary. Boundary is a circle with radius r, right? Squared. So how do you come up with a boundary? Does anyone know? Need parameterization of this boundary? X equals r times cosine theta, r times sine theta, right? Is r changing? R is not changing. Theta is changing from where to where? 0 to 2 pi. That's your parameterization. Now turn this one into parameterization. So theta going from where to where? 0 to 2 pi. What is x? R times cosine theta. What is dy d theta, right? What is it? Negative, or it's a positive sign, right? R cosine theta. D theta. This is what you have to compute, correct? So let's go, and this is r squared, 0 to 2 pi, and here's a cosine squared theta. Anyone remember how to handle cosine squared? There's some trigonometric fact. 1/2 plus, 1/2 sine, now cosine, 2 theta, d theta, right? What happened if you integrate 0 to 2 pi of cosine 2 theta? If you have done many of the homework, you probably remember, oh, that's actually 0. Everything cancel, 0, right? So this is r squared, 0 to 2 pi, 1/2 d theta, and what did I just say about the remaining integral? 0. You will find that it's a 0. So what is the integral of this one? 0 to 2 pi, 1/2. That's just pi, right? It's pi r squared. All right. Some magic was just done with that line integral. So let me give you a next problem, and you will do the magic yourself, right? Next one is ellipse. Does anyone remember the area of an ellipse? So here's an ellipse. is got to be related, some sort of generalization of pi r squared, right? Because ellipse is a special shape of this one, correct? So here's an ellipse. If it is given by this formula, what is the x-intercept? If it is like this, what is the x-intercept? A is x-intercept, right? What is y-intercept? Plus minus b. You can easily verify that, oh, 0 comma b, that does it. A comma 0, that does it, right? An ellipse looks like this. And what are we calculating? Area inside that, right? So area inside, that's it. Area D. Area inside that, how do you formulate with a double integral? 1 in there, dx dy, right? That's the area of this one. That's what's at stake. Then what do we do about this one? Yeah, Green's magic. That's here it is, round D. And what is the differential form here? The easiest one? X dy. Now what do you have to do to compute the line integral? You have to parameterize it, right? So let's parameterize it. What is x and what is y? This time there's no r. This is a and b, right? We want this one to be cosine. So you have to cancel that a by throwing in like this. Now it's the standard parameterization of an ellipse. How about y? B sine theta. So if you stick that in there, do you see that a cancel? X and a, right? A squared cancel. Leaving just cosine squared. How about this one? Go in there. B squared cancel, right? Leaving just sine squared. You verify that's 1. Therefore, it's the correct parameterization, right? So I got parameterization. You have the line integral to calculate. And that's your first and the only exercise today. Compute the area. How was it? Did you get pi times a times b? Yeah. So if a and b are equal to each other, what is it called? They're called circle, right? A and b are equal to each other, and then it's a perfect circle, right? And a and b are equal to each other, then pi r squared. It generalizes like that, right? Very nice. And what was the circumference of the circle? 2 pi r, right? And how is this one generalizes? People gave up. Nobody knows. Yeah. No one has found out. Yeah. And they proved that you will not succeed. Yeah. They proved it. Yeah. Yeah. So today's colloquium talk in 12 is called differential Galois theory, is burst out of the frustration. So how do we justify we should stop trying? So mathematicians prove that the circumference of the circle is not written down in terms of the function we know, exponential, logarithmic, and sine, and you cannot write it in terms of those things. So it is proven, and that give a birth to subjects called differential Galois theory. And one student who involved in that research, and Dr. Hessinger, is giving a talk about that area today. But area worked, not the circumference. The arc length was famous unsolved problem, and do not solve problem actually. All right. You agreed he's doing some magic in there? Everything? Here's You know, you got to clap under what this magic is doing. So it's fundamental theorem of line integrals, right? That is already doing some magic. The crazy word calculation is done, and down there, Green's theorem is calculating. Just you see the loop there? It's going through a vector field. The woman's vector field is going through that, and it's a skull. It's everything. It's wow, magic is just done. This is amazing, and even more miraculous thing is done in the next section called Stokes theorem. Yeah, but we're gonna have one day break before we hit by this.